this class, we'll talk about the primal-dual relationships. Given the primal problem and this dual problem, we have them in the matrix form, and then we have the weak duality property. If X is a feasible solution for the primal problem and Y is a feasible solution for the dual problem, then we always have the objective function Cx to the primal problem is always less than or equal to the objective function to the dual problem Yb. As a consequence, if X is a feasible solution for the primal problem and Y is a feasible solution for the dual problem, and they are equal, the objective functions are equal, then we say X and Y are both optimal solutions to their corresponding problems. In contrast, we also have the strong duality property. We say if X star is an optimal solution for the primal problem and Y star is an optimal solution for the dual problem, then we always have their objective functions Cx star equals Y star B. So combining these two properties, we say Cx is less than Yb for feasible solutions if one or both of them are not optimal for their respective problems, whereas equality holds when both are optimal. Okay. So from these properties, we say the following are the only possible relationships between the primal and dual problems. First, if one problem has feasible solutions and a bounded objective function, then so does the other problem. So both the weak and strong duality properties are applicable. Second, if one problem has feasible solutions and an unbounded objective function, then the other problem has no feasible solution. Third, if one problem has no feasible solution, then the other problem has either no feasible solution or an unbounded objective function. This means that if one problem has a feasible solution, if one problem has an optimal solution, then so does the other. Otherwise, the relation does not hold. Okay, so in general, we know we can use the simplex method to solve primal problems. The weak duality property describes the relationship between any pair of solutions for the primal and dual problems, where both solutions are feasible for their respective problems. At each iteration, the simplex method finds a specific pair of solutions for the two problems, while the primal problem, a solution is feasible, but the dual solution is not feasible. We have a property describes this situation and the relationship between this pair of solutions. But first, let's look at the relations of the solutions of these types of problems. In a dual problem, the functional constraints are of the form Ya bigger than or equal to C. To put it into a standard form in the linear programming problem, we subtract the surplus from the left side of each constraint j. This surplus, when we move all the values to the left-hand side, zj minus cj is simply the sum of aijyi minus cj. So in the standard form, bigger than or equal to 0, the surplus cj minus cj plays the role of the surplus variable for the constraint. Therefore, augmenting each solution yields a basic solution, while we still have the variables y1 through yn with surpluses z1 minus c1, z2 minus c2, up to zn minus cn. Since the augmented form of the dual problem has n functional constraints and n plus m variables, each basic solution has n basic variables and m non-basic variables. One of the important relationships between the primal and dual problems is a direct correspondence between their basic solutions. The key to this correspondence is equation 0 of the simplex tabular for the primal basic solutions. So if we look at the equation 0 in the simplex tabular, we say that, well, we introduce the slack variables for our original problem, and then our variables consist of decision variables x1 through xn and then the slack variables xn plus 1 up to xn plus m. And then the correspondence for the dual problem is that we have m variables for the dual problem, y1 through yn. They are actually in correspondence with our slack variables xn plus 1 through xn plus m. And then the surpluses z1 minus c1 up to zn minus cn are actually in correspondence with our decision variables x1 through xn. This holds at every iteration of our simplex tableau. So a key insight here is that the dual solution read from equation 0 must also be a basic solution. This is because the m basic variables for the primal problem are required to have a coefficient of 0 in equation 0, which thereby requires the m associated dual variables to be 0. So for any problem, no matter is a primal problem or a dual problem, we say the original variables xi are the primal variables. In correspondence in the dual problem, they correspond to zj minus cj, the surplus variables. And on the other hand, the slack variables in the primal problem xn minus m plus I to xn plus m corresponds to the original variables yi in our dual problem. So from this, we have the complementary basic solutions property. We say that each basic solution in the primal problem has a complementary basic solution in the dual problem, while their respective objective function values z and w are actually equal. And then we also have the complementary slackness property. Given the association between variables, the variables in the primal basic solution and the complementary dual basic solution satisfy the complementary slackness relationship as below. In the primal problem, the variables are divided into basic and non-basic variables, while in the associated dual problem, the variables are divided into non-basic and basic. And the basic variables in the primal problem corresponds to the non-basic variables in the dual problem, whereas the non-basic variables in the primal problem corresponds to the basic variables in the dual problem. Next, we also have the complementary optimal basic solutions property. Each optimal basic solution in the primal problem has a complementary optimal basic solution in the dual problem, while their respective objective functions values are equal. So basic solutions can be classified according to whether they satisfy each of the two conditions. And for each of these conditions, we have different names for the solutions. And one is the condition for feasibility, namely whether all the variables in the augmented solution are non-negative. The other is the condition for optimality, namely whether all the coefficients in equation 0 in simplex method are non-negative. So if we have a solution based on whether it's feasible or if it satisfies the optimality condition, we have different names for these solutions. So if a solution that is feasible and also satisfies the condition for optimality, we say this is actually the solution we want. This is the optimal solution. However, if the solution is feasible, but it doesn't satisfy the condition for optimality, then we say this is a suboptimal solution. And then suboptimal simply means it satisfies all the non-negativity conditions, but it's just not the optimal. There is something to be improved. On the other hand, if a solution is not feasible, meaning that there may be some negative variables. On the other hand, if it satisfies the condition for optimality, then we say this is a super optimal solution. This is too good because the variables may be too large. They do not satisfy the feasibility constraints. And then, so if the solution is neither feasible or satisfies the condition for optimality, then this is nothing. We do not have a name for it. So basically, we generally care about optimal solutions or super optimal solutions or the suboptimal solutions. Okay, so then as we saw earlier, the relation between primal basic solutions and dual basic solutions, we say that if a primal basic solution is suboptimal, then the corresponding complementary dual basic solution is superoptimal. If the primal basic solution is optimal, then the complementary dual basic solution is also optimal. On the contrary, if the primal basic solution is superoptimal, then the corresponding dual basic solution is suboptimal. If the primal basic solution is nothing, then same for the dual basic solution. So this is the relation between them. From these relations, we can actually see what the simplex method does is, given a primal problem, we start from a suboptimal solution that is feasible but does not satisfy the optimality conditions, and then start from the suboptimal solution, approach the optimal solution. And then in correspondence, the dual problem will while the solution is suboptimal, and then we can apply some method to approach the optimal solution. Whereas the suboptimal solution for a primal problem corresponds to a superoptimal solution in the dual problem, and then vice versa. Okay, so at the final iteration of the simplex method, it simultaneously identifies an optimal solution x star for the primal problem and a complementary optimal solution y star for the dual problem, where we have the objective functions cx star equals y star b. The y star i's, reading from the equation 0 in the final simplex tabula, are actually called shadow prices for the primal problem from the economic point of view. For example, if we have this linear program problem of maximizing z equals 3x1 plus 5x2 with all these conditions, and we can build up a dual problem of minimizing y. And then at each iteration of the simplex method, reading from equation 1, we can find out correspondingly the BF solution for the primal problem and then the corresponding dual solution to the complementary dual solution to our dual problem. For example, at the beginning, we say, well, our initial BF solution is x1, x2 equals 0, and then x3, x4, x5 equal to 4, 12, 18. And then also reading from the first row, we say, well, our variables in the dual problem, y1, y2, y3, corresponds to the slack variables. They take value 0, 0, 0. And then cyclically shift from the beginning, the rest of the variables in the dual problem take values -3, -5. So we say, in this example, the BF solution satisfies the non-negativity condition, so this is feasible, but it fails the optimality condition, so it's a suboptimal solution. On the other hand, the Y's do not satisfy the non-negativity condition, so this is a super optimal solution. And then after iteration, after we do the optimality test to find the maximum coefficient in absolute value, and then do the minimum ratio test to decide the leaving basic variable and entering basic variable, we got a new table of the simplex method. And then from this new table, again, we can read the solutions to the primal problem x2, x3, x5 equal to the right-hand side. And then the basic variables are x1 and x4. They take values 0. Correspondingly, reading from the first row, we say, in this case, the complementary dual solution is y1, y2, y3 corresponding to slack variables x3, x4, x5, 0, 5 halves, 0. And then cyclic shift 3, -3, 0. So this is the complementary dual solution. And then again, we say this is feasible but not optimal. So this is suboptimal. And then the solution correspondingly for y is superoptimal. So we can repeat this procedure, and at each iteration, we find correspondingly the solution to the primal problem and this complementary dual solution. At this point, finally, we have all the variables non-negative, and then it passed the optimality test because the first row all have coefficients non-negative. So this is our optimal solution. And correspondingly, for y's, all the values are also non-negative, and then the right-hand side is also positive. So this is also an optimal solution for our dual problem, and they share the same value of the objective function 36. Okay, so next let's look at some economic interpretation of the duality. So first, if we look at the original primal problem and the dual problem, we say that in the dual problem we have this YB. So each of these YIBI can thereby be interpreted as the current contribution to profit having BI units of resource I available for the primal problem. In this case, variable yi is interpreted as the contribution to profit per unit of resource I when the current set of basic variables is used to obtain the primal solution. So first, as we defined earlier, the shadow price. So what is a shadow price? We say the shadow price for resource I, denoted by yi star, measures the marginal value of this resource. That is, the rate at which z could be increased by slight increasing the amount of this resource being made available. The Simplex method identifies the shadow price such that yi star is actually the coefficient of the i's slack variable in equation 0 of the final Simplex tableau. As we defined earlier, we say these yi stars are actually the shadow price. So yi values in the optimal solution for the dual problem are exactly the shadow prices for the resources in the main problem. For example, again, we consider this table. This is already the final Simplex table. All the values are optimal. And then at this point, we say that this corresponds to our original linear program problem. And then reading from the first row, we can see that y1, y2, y3 corresponds to the values of the slack variables. So y1 equals 0. This means the shadow price for resource 1 is 0. Similarly, y2 equals 3/2. The shadow price for resource 2 is 3/2. And then the shadow price for resource 3 is 1. Okay, so what does the shadow price tell us? We say in this example, y1 equals 0 because the constraint on resource 1, x1 less than or equal to 4, is not binding on the optimal solution 2, 6. It is not an equation. There is a surplus of this resource. Therefore, increasing B1 beyond 4 cannot yield a new optimal solution with a larger value of z. In economic terminology, such a resource is a free good. The price of goods that are oversupplied must drop to 0 by the law of supply and demand. This fact is what justifies interpreting the objective for the dual problem as minimizing the total implicit value of the resources consumed, rather than the resources allocated. On the other hand, the constraints on resources 2 and 3, 2x2 less than or equal to 12, and 3x1 plus 2x2 less than or equal to 18 are binding constraints. At the optimal solution, these inequalities are strict equations. Because the limited supply of these resources binds z from being increased further. They have positive shadow prices. Economists refer to such resources as scarce goods. So the kind of information provided by shadow prices clearly is valuable to management when it considers reallocations of resources within the organization. For example, practically, it is more likely to purchase more of the resources of a higher shadow price because potentially they would contribute a higher profit. So this is the primal dual relationship, and then is economic interpretation.